Hello, everyone, and thank you for attending Lab Manager's Lab Design Digital Summit. My name is Mary Beth DiDonna, and I'll be moderating this discussion. The Lab Design Digital Summit is a series of informative webinars that brings together lab management leaders with experts in the laboratory and healthcare design community. This free, full-scale digital event allows attendees to participate in educational sessions led by top experts in the lab design build field from the comfort and safety of their own homes. Welcome to this session, Net Zero Labs. Laboratories are the most energy-intensive group of buildings to operate. To prevent catastrophic climate change, we need to reduce our emissions to zero as soon as possible. Fortunately, this is not only possible, but also relatively inexpensive. Moving our lab buildings to be all electric and reduce energy use overall produces buildings which are simpler to operate, cleaner for the world, and better isolated from future energy price volatility. This presentation will provide a practical definition of net zero, explain electrification in support of that goal, and discuss major features of laboratory buildings which can be designed to support it. In addition, financial rules of thumb for construction and operation of all electric buildings will be compared to historical and projected energy prices. We like our webinars to be very interactive, so we encourage you to send us your questions at any point during today's webinar. And there's also a poll on the screen if you would like to participate. Our speaker will address your questions and comments during the question and answer session following his presentation. To ask a question, simply type your query into the question box, which is located on the right-hand side of your screen. We'll try to address as many questions as possible during our time together, but if we run out of time, I will forward any unanswered questions to today's speaker, and he can respond to you directly if possible. Additional resources and handouts are also located on the right-hand side of your screen. I'd like to remind you that this webinar recording will be available for free on-demand download shortly following this live presentation. And I would also like to extend a special thank you to our sponsors whose support allows Lab Manager to keep these webinars free of charge for our readers. So with that, I would like to introduce our presenter for this webinar. Matthew Fickett leads SGA's Science and Technology Group, which provides laboratory design expertise to support the millions of square feet of science buildings the firm designs annually. He supports project teams at every phase of design and construction and is involved in both direct laboratory design and the design and repositioning of buildings to support future labs. A primary goal of his work is to ensure that these labs don't just meet current needs, but are adaptable for rapidly changing science and sustainable for the benefit of the whole world. Matthew, thanks for joining us today.
Thank you. It's great to be here. Thanks for that introduction. So what I want to talk about today are net zero laboratories, and this is a phrase I suspect most of you in the audience have heard. I see that half of you are designers and builders of labs, so I hope you've all been talking about this already. I want to start by saying, back up to the first principles. Why do we care about this? Why is this such a push? Why should we worry about it? So the key metric here is the energy used by our buildings. The units on the left that look so complicated is just energy per square foot per year. And existing labs are way up at 500 on average. There's a huge error bar on that. New laboratories, we're in between 100 and 200 if we're doing a good job. If we're really knocking it out of the park, we can be down around 100. So these are nice numbers. What do they mean? How can we ground them to something that you're used to? Well, if you buy a really bad house, like I live in a house from the 1800s with almost no insulation, we're here at about half of what a new lab is using. Good modern housing, way down there. And if you have a standard like passive house, we're barely eking along at the bottom. So if you are in charge of a lab or the design of a lab and you can do anything about that bar on the left, if you can knock 20% off of it, much less all the way to net zero, you will do more good doing that than anything you will ever do at home. So I think focusing on what our labs are using is one of the most important things we can all be doing here from a sustainability point of view. So the ambitious goal, net zero, not just a little better, but all the way better. There are a lot of fairly complicated definitions floating around and people argue about the footnotes. I want to try to establish a pretty straightforward one. So if you're net zero, you emit no carbon. You operate your building and there's no carbon going out into the world. So to put it a different way, don't litter. We learned this rule a long time ago we obey it for trash you're holding in your hand, our buildings should obey the same rule. So to do it diagrammatically, here's the world. The sun shines on the world. The world gets warm and emits heat. That's the world without us. That's what's already going on. And our goal is not to change that. So when we show up, we're in this boundary. From a science point of view, we could say the system we care about is inside that boundary. And we want the inputs and outputs to stay the same. Sun comes in, heat goes out, nothing else happens. So you put a building in there, you need to power it. The way we do it here, right? You've got solar panels on the roof, and that is lovely because you're still only getting solar energy in and you get heat coming out. Just sunlight turns into heat. It just happens to be electricity for a minute along the way. You can do the same thing if you put your solar panels down the street, the next state over. It doesn't matter what that bubble is, how wide that boundary is, as long as everything you're doing to turn sunlight into heat just lives there and you're only emitting it as that heat energy. Wind turbines I include because there's some people, it is not obvious that sunlight moves air, air moves the wind turbine turns into electricity, the electricity turns into heat. It's the same cycle. In fact, that holds true for all renewable energy. It's all powered by the sun. So you don't break the rules as long as everything you're doing is renewable energy. So far, I hope so good. By the way, I have the ability to see questions you might type in. So if there's anything I'm saying that is not clear as we go along, please feel free to interrupt and point it out. I would love to discuss as we go. So what do we need to do to make the building work in this diagram, aside from glue solar panels to the roof? Well, the key feature, right, is that we obey these rules we set up. This breaks the rules. This is how most of our buildings work now. There's an oil pump pulling oil out of the ground somewhere, or coal, or your fossil fuel of choice, natural gas. There's a pipe somehow from the refinery to the building. We burn it, and we emit carbon. We emit that smoke. So we've broken the rules because that boundary box we have, the only thing you're allowed to cross it with is sunlight and heat. And when we pull carbon out of the ground and dump it into the atmosphere, we're breaking our rule. So this is not allowed. This is not a way to get to net zero. And I'll point out a different way. This is also not renewable, right? My earlier rule was any renewable energy counts. This is not. So, right, it breaks the don't litter rule. We are littering. So if you want the building to work, right, if it has to run on renewable energy, the only kind of renewable energy there is electricity. So you have to have an all electric building. It is not possible to generate fossil fuels in a renewable way, and it's not possible to use them in a renewable way. So in this case, we can see that a necessary condition for getting to net zero is having an all electric building. So looking at just the building itself, once we zoom in, this is what we care about, right? We are designing a building. So we've got beautiful solar panels on the roof, and I think we've all heard the environmental mantra on the recycling bins, right? Reduce, reuse, recycle. We can reduce the initial load. And the first thing that you can look at when you look at a lab building is that the major source of all that energy that we're burning is space conditioning for heat. The reason lab buildings are so energy intensive is that we have that 6 air changes per hour going through the laboratories, and more than that, usually getting exhausted through the various systems we have. So the energy we use to condition that heat is the main reason our lab buildings are so expensive on an energy front. So a lot of that right now is natural gas. You have an air handler, you have a natural gas line to it, you're heating the air with natural gas. What we need to do is get to a heat pump. And a heat pump is not a mysterious object. It is something that you have probably in your house. Your refrigerator is a heat pump. It's just a way of using electricity to move the heat around instead of turning the electricity into heat. And because you're just moving heat from one place to the other, you can be using it either to quote unquote generate heat or cold. So your fridge gets cold inside, your kitchen gets warmer. Your window air conditioner is just moving heat from inside your room to outside your room. So there's no reason you can't do the same thing on a whole building scale. So you can say, all right, the air handler in the penthouse of this building has a heat pump. We're using electricity to heat or cool the incoming air. And I want to emphasize at this point, we'll get into some of the cost details later, but I'm sure many of us have had the experience of moving into a house only to have the disagreeable surprise that it's got electric baseboard, and you realize your electric bill is going to be huge. That is not what we're talking about here. That form of heating, electric resistance heating, is 1 for 1. We say it has a coefficient of performance of 1, meaning for every watt of electricity you buy, you get 1 watt of heat in your space. With a heat pump, you're not turning the electricity into heat, you're using the electricity to move heat. So you can get a coefficient of performance of 3 or 4 or higher. The bigger your heat pump, the more efficient it is. There are grid scale heat pumps in Europe that are getting a coefficient of performance of 8 or 9. So for every watt you spend on electricity, you're getting 8 or 9 watts of heat in your building. At a building scale, we're probably talking in the 5 or 6 range. It's still really good. You're taking that energy and multiplying by 5 or 6 times. It sounds like you must be making a mistake to say it, but that means the heat engine there is 500 or 600% efficient. Normally, we like to think you can't do better than 100% efficient without breaking the laws of thermodynamics, but we're cheating a little by stealing heat from the environment. So all that to say, you've put in a heat pump. Now you can either heat or cool with the same piece of equipment because you're providing that heat pump. It's just a heat mover. You can run it both ways. So you're providing conditioned air. For all the diagrams in this presentation, I'm pretending it's winter outside. So we get blue cold air. We heat it up coming in through the air handler, and we're providing that nice hot air into the lab building. But as I discussed, there's a terrible problem in lab buildings, which is fume hoods, where we take all that beautiful conditioned air and we throw it away almost as fast as we can bring it in. So I could spend days talking about all the different ways you can reduce the space conditioning load in a lab building, but one of the really big ones is those fume hoods. So I'm going to focus on them for a few minutes. So the first thing you can do to reduce this load is use less air, right? And hopefully all of you have fume hoods. You're approaching the 50 feet per minute face velocity. You've got self-closing sashes. We're getting out of the habit of storing chemicals in hoods that could be in chemical storage cabinets. Everything you can do to reduce the amount of air flowing through those hoods reduces the size of the air handler, reduces the amount of energy that you have to use to condition the air. In general, you're making really good progress just focusing on reducing those hoods. But you can go a step farther. If you have filtered fume hoods, which I suspect some of you have experimented with, and I wish I had asked you that question too as you came in the door, then the air doesn't leave the building at all through the hood. The hood is just recirculating that air into the lab through a filter that's tailored for the chemical mix you're using. And then you can take the air from the lab back out through the air handler, and you can do heat recovery on the way out. So all the energy you put into heating the air on its way in, you can take that energy back, and pass air back out to the outside. And the efficiency for a heat exchanger can be in the upper 90% range. So you've taken your 1 watt of electricity, you've made 5 or 6 watts of heat on it, and then when you send it back out the door through the air handler, you get to keep 4.5 watts. So you're really getting quite a lot of mileage out of that 1 watt if you can get it back out through a heat recovery system. I'll talk for a minute here about the filtered fume hoods because I think that's a bit of outside of a lot of people's experience. The chief restriction here is that you have to tailor the filter set in the fume hood for what you're working with. And a lot of folks in the laboratory world I'm sure you've all had a researcher say to you, but I don't know what I'll be doing in the fume hood. The fume hood is there for me, and I'll put anything I want in it, and any kind of acid or chemical or poison or whatever, doesn't matter. The hood will just make it go away. Someone else's problem when it's outside the building. I think that kind of thinking needs to change, but it doesn't need to affect the ability to do successful science in the laboratory. We have lots of places in the lab where there's some rule about what you can pour down the drain or what tool is compatible with what chemical or something else. So you can say in a lab, if you have a known process with a known chemical set, you make sure the fume hood filters are appropriate for it, and you do that process in that hood. And that's fine because that air is just recirculating. You're not spending your energy budget throwing that air away. You can actually afford to have more hoods in the lab than you might be used to and still come out ahead on the energy bargain. Then off to the side, you can still keep, if you need them, some exhausted hoods that give you wide open blank check to do whatever you're used to. But that move to recirc hoods is really key for reducing the conditioned air load in a laboratory setting. So having outlined this workflow, the first question, of course, is what does it cost to go to an all-electric building? And short answer, it's not a lot. It is an additional cost right now. The systems we're talking about are a little more expensive, so 1 or 2% more. This is not just the move I talked about. There are other systems in the building that I can talk about if we have some extra time at the end. But in general, you can get an all-electric building built for a couple percent more right now. You also have to think about what the operational cost is going to be. That picture is a little less rosy right now. Operating an all-electric building is 10 to 20% more than operating a building that's what I'll call conventional or traditional construction, where it's mixed. And a lot of that is due to the current energy prices for each. We know that natural gas is historically cheap, and that certainly pushes that down. But there's an important caveat, I would say, to this, which is the future is changing. You've heard a lot of people probably talk about carbon taxes, and I want to talk about what that impact is likely to have on our buildings in the future. And as we have this conversation, think about the lifespan of the buildings you build or operate. A relatively short commercial lease is single-digit years. A long one might be 10 years or more. A building is going to operate with the same air handler for 25 or 30 years before the air handler gives out. So when you're choosing building systems right now, you're not choosing them just for today's world. You're choosing them for the world you expect to be operating in conceivably decades from now. So it's worth trying to think seriously about what you expect that to look like. So talking about that future in a little more detail. Here is a graph, and I'm going to talk not about the specific spot price of electricity or gas per kilowatt hour, per cubic foot, or per therm, or anything like that. I'm going to present a metric, which is how much would it cost to operate the same building with modern up-to-date equipment, whether it's gas or all electric. And that gas building isn't really just gas, right? You still have electricity for your electrical outlets and some other uses. But to simplify the picture, we've got the old gas building and the new electric building. So, excuse me. The electric building, you can see, has been pretty steady over the last 20 years. There's been a slight uptick in electrical prices. There's a little seasonal variation that's not totally coming through in this simplified data set. But by and large, if you had an electric building 20 years ago, you're not going to be completely shocked about what you're paying for the electric building today. The traditional building has had quite a noisy history. You can see there was a spot there in the late, I don't know what we call that decade yet, call it around 2008, where the price was nearly double what it is to operate the electric building. And then around 2015, you were in a really good place with your traditional building. And since then, it's sort of whipped back and forth a little bit. And my graph doesn't come quite up to the present moment. That electric line should spike up a little bit. The gas line should spike a little more down to say we're currently in the spot where the electric world is 10 to 20% more expensive. But the point I want to make with this graph is the current moment is not representative of the past, and I also don't think it's representative of the future. There have been some times where you would have been in a much better place in the past, not just for price, but also for certainty. And if you're a building owner or an operator, being able to predict your utility and energy costs over the long term is a really valuable thing. I'm sure folks, whoever's left holding the bag, whether it's landlord or tenant, depending on your deals, it's not fun when you get one of those 2008 moments where the price of energy has doubled compared to what it was a couple of years before. So as we get into the future, I think it's reasonable to expect these things will continue. And I'm not just basing that on the idea that electricity has historically been smoother. It's that electricity is really an amalgamation of several sources, right? It's the current price of photovoltaic power and wind power and hydroelectric power and natural gas being burned for electricity. So it is, you're buying a fund, as it were, of generation technologies. You're also buying into a fund of carbon emissions. And I don't have a graph for this, but I want to make the point anyway, which is some people have probably been sitting in the back waiting to point out that you can make your building all electric all you want. And if electricity comes from a gas plant down the road, have you really made any progress? The answer is yes, you have. And there's two reasons for that. One is the gas plant down the road burns the gas a lot more efficiently. The efficiency of a combustion engine scales with the size, and the gas plant is very much larger than any burning situation you have in your building. Also, the future does not look like the past. There's a lot more renewable energy being generated, and in fact, we expect that transition to accelerate. The state of Massachusetts, where I am, used to have a law that said the utilities have to add 2% per year of renewable energy, which was very nice. The utilities have been adding more than that because it's actually cost effective for them. So they're ahead of what's required by legislation just from a pure capitalist self-interest. And so the legislature just passed a new law to make it 3% per year so that the law at least can keep motivating them. So the Massachusetts grid is going to be fully renewable in a few decades, I suspect sooner again than the law requires. So if your building is all electric, it will be fully renewable when the grid catches up. If you're still burning gas, you don't get that benefit because, again, there's no way to renewably generate gas. That's not a thing. That was a little bit of a tangent from this slide. Sorry about that, but I think it's an important note. So that was on the generation of power. There's a whole separate topic, which is what that big black warning label was about, which is there is a world coming where you pay for the pollution your building emits. So the states that are highlighted here, there are laws that are either in effect now or scheduled to come into effect, which charge you for carbon emitted by any business or function that you own. So they're just getting started. I think we're used to the states that are highlighted here leading that kind of legislation, so that's not really a surprise. It's on the table in a couple additional states, which is great. And there's a third category where we have building specific legislation, not just general carbon tax, but the states that are outlined here, Massachusetts, New York, California, Washington, there are municipalities and larger subsections of the state in these states that have actually banned the use of natural gas in new construction, or they've implemented building codes that incentivize electrification or require electrification of buildings. So when you look at this map, you can see, I think, where things are going. You can also look at it and say, well, that's a fairly small corner of the map and there's not much going on there. But these dots are the top life science research clusters from last year. And there's a high degree of overlap between the states with this kind of regulation and the states where we try to build laboratories and operate laboratories and do science research. So I think it is very relevant for those of us in the lab building world to pay attention to where this is going. By the way, the Denver Boulder dot looking lonely in the middle of a gray state there, they have actually a carbon tax legislation just in that municipality. So don't want them to feel left out if there's anyone here from Colorado. I think the most interesting future trend, I'm going to highlight New York City here because I think they're the best known for this. There's an ordinance called Local Law 97. And that ordinance, which is in effect, charges buildings for carbon they emit over a certain threshold. And the law is written so that that threshold decreases over the future, so it'll affect more and more buildings. And it's a non-trivial amount. I'm not going to try to do the math live on camera, but it's hundreds of dollars per ton, and buildings emit thousands to tens of thousands of tons of carbon per year. So add a couple more zeros to that, and it's easy to imagine that your building could pay hundreds of thousands or millions of dollars in fines per year. And this is unlike most building codes in that it applies to existing buildings. Most of the time when we see the nice building code legislation about insulation levels or ventilation rates or some other sustainable initiative, we can think, well, great, I got in last year's code, I don't need to worry about that. That's not the case here. This legislation, like the other carbon taxes, applies to your building no matter when it was built. It applies to what you're doing. So to the extent that we anticipate that coming in the future, and if I zoomed out this map to show what colors Europe and Canada are, you could really get a sense of how much it's coming, because as usual, the US is a little behind on that. I think to the extent that you think that's coming in your future, it makes a whole lot of sense to plan buildings to not get fined or taxed under that structure. So, summary of what we're talking about here. Why am I doing this presentation at a lab conference? Because I think the labs are what counts. The labs are where we use most of the energy. And if we can make a difference in the laboratories, we'll make more of a difference than anything we can do anywhere else. My definition for net zero, don't litter in the world. Just don't put carbon out in the air. Don't make your building something that's polluting. It's pretty straightforward, and the goal we all have to get to sooner or later, hopefully sooner. To do it, the building has to be all electric, and to make that practical, reduce the loads in the building. And it looks like we'll have some extra time, and there are lots of other interesting ways we can talk about to do that past fume hoods, but they're the big one. And then the stick on that, what's coming that's going to force this? The law is going to start charging people for putting carbon in the atmosphere. Sort of the way we have a fine for littering, we're going to get a fine for letting your building litter. So even if you're not motivated to try to save the world altruistically, if you expect your building to survive very many years into the future, it will be affected by this, and we need to move towards it. So thank you for that. And I think we've got plenty of time for questions, and I'd really like to get into that.
All right, great. Thanks very much, Matthew. So as Matthew said, at this point, we're going to move into our Q&A session with the audience. So those of you who, if you may have joined us late in the presentation, you can send in your questions by typing them into the question box, which is located on the right-hand side of your screen. And even if you don't have a question, if you have a comment or would like to tell Matthew how you enjoyed his presentation, you can put that information there as well. So Matthew, the first question we have from the audience is, what other building systems, aside from air heating and cooling, would need to be converted to electricity?
Yeah, and I hinted at this a bit, but I'm glad to dig into it. there's a lot of infrastructure that in a building that's focused on moving heat around. So you have hot water, where you've got systems that for domestic and for laboratory use and for space conditioning use, which all rely on hot water at a certain temperature. And a heat pump hot water heater is a great application for that. I should reverse it. This is a great application for heat pump hot water heaters. I recently installed one in my house. They work just fine. It's the same principle as all the other heat pumps. You're just using the heat pump to move heat from the air into the water. The opposite end of that spectrum is when you have a dedicated chiller. And again, that can be a heat pump or it can just be an electrically powered chiller. We have evaporative chillers on the roof of buildings now that just draw on electricity. That's still allowed. That still works. And then you've got all that. I get questions, I guess, on two sort of subsidiary topics sometimes where people talk about what about natural gas in labs? And I am really interested in, I wish I could like ask everyone to put their hands up, but I haven't put a Bunsen burner on a lab bench in something I've designed in quite a while. I've seen a lot of institutions start to really push against allowing internal combustion for indoor air quality reasons, which I think is great. So there's a small subsystem that I think ought to be electrified just for the occupants' quality of life, much less this whole goal. I can see more questions coming in, so I should probably stop being so wordy and let Mary Beth tell me what's going on.
It's all good. We actually have plenty of time left for questions. So, if you want to give a more thorough answer, that's perfectly fine. But thank you for that. We have another question that says, aside from fume hoods, how else can a lab be designed to reduce demand on the air system?
So this is much more at the architectural stage, which, is easy for me because I'm an architect. It's a little harder when you're just operating the lab that's already been handed to you. But the key thing that I focus on is trying to reduce the amount of square footage that is lab. So in some older labs, you'll see the bench and the write-up space and maybe some meeting space off in the corner, all inside the lab boundary. And you're doing 6 air changes per hour through all of that with single pass air. So the narrower you can draw your lab boundary, the better it is for everything you're doing. It's safer for the occupants, but it's also much less energy intensive. And if you're in a situation that allows it, you can actually supply air to the office side, cascade it to the lab, which you've drawn very narrowly, use that as bonus supply air. So you can significantly reduce the air load that way.
Okay, great. Thank you. We have another question that says, how does switching to electric affect building layout?
This part's mostly good news. This is easier. When you just have one system, one way of moving energy around in a very small degree, your cores get smaller and simpler, right? There's no natural gas piping to deal with. There's no exhaust flues from water heaters that are burning gas or heaters that are burning gas. So you simplify and reduce the size of your building cores. Your penthouse sometimes can get smaller as you work through the air handling equipment. So in general, building infrastructure components get smaller and simpler. That one is pretty straightforward.
All right, great. Thank you. Here's another question that says, how much bigger does a building's electrical service need to be?
The right answer is it depends, but the real answer is in many climates, not at all. So we get this fear a lot with folks who feel like they need to upgrade the electrical service to go all electric. And taking this question back to some very clever engineers, I've been very happy to find out that for most buildings, your electrical service is already sized due to the cooling load in the summer. So we're already mostly using heat pumps in an electric situation to cool our buildings or to run the cooling towers. So when you get into the winter, Of course, you're heating instead of cooling, but your heat load is almost always going to be smaller than your cooling load because you get free heat from people standing around emitting heat, from lab equipment emitting heat, from computers emitting heat. Second law of thermodynamics says everything we do in there is just emitting heat all the time. So the amount of energy you have to spend in the base building system to heat it is almost always less than what you would have to spend to cool it. There are exceptions if it gets really, really cold where you are. If you're in Chicago, I'm sorry, my answer doesn't apply. But in general, you don't have to change the building electrical service to go all electric.
All right, great. Thank you. We have a couple more questions here. Are there any funding resources for government labs that you can mention that may be available?
The funding pathways inside the federal government are a complicated topic that I'm not sure I'm competent to address, but I can tell you some places to start looking. Lawrence Berkeley has done a ton of work on all electric buildings, and I think there are one building finished and one under construction in terms of all electric laboratory buildings that they've built on the Lawrence Berkeley campus. I know they are a terrific resource for everything technical, and I'm sure they're also plugged into any funding resources. I'm sure they have availed themselves of any funding resources that are applicable to a government entity. So they would be a good one to point you in any direction that you could use. For the folks who aren't a government building but still have the same question, on the state by state level, there are often resources worth looking into. So in Massachusetts, there's the Mass Save program that's administered by the state but funded through a charge on utility company bills, and that offers incentives. There are also incentives, other separate incentives at some of the local levels.
Okay, great. Thanks very much. We have one last question. Thank you, Matthew, for the explanation on converting buildings to electric and how that is beneficial. How do you feel about the positive effects of adding solar power?
Torn is the short answer. On the one hand, it's very clear. You have a building, you put solar panels on the roof, you've done something good. Your building is producing electricity with no emissions. On the other hand, I think it sometimes gives people a false sense of progress. In general, the footprint of a building, especially a lab building, you can cover 100% of the roof with panels and you're going to add like 2% of the building's utility draw. So you need a football field somewhere covered with panels to help with it. As we reduce the load of the building, we get closer and closer, but even some really brilliant net zero lab buildings that I know of, the roof is covered with photovoltaics, and so is the parking lot, and so is the field across the street. So I like it from an immediate results point of view. I like it from a kind of advertising point of view. It generates awareness, right? And awareness matters. It's important that people know what we're doing. On the other hand, it's maybe less effective than people think it is. I think you can, my diagram was rough but honest in that a single good-sized wind turbine will run multiple buildings. The amount of power available from a wind turbine is just phenomenal, and power scales as the cube of rotor diameter. So those big wind turbines offshore are just good for running whole campuses. So if I had a client who I could advocate for this for, I would say buying utility scale wind is probably a better use of resources. At the same time, I would advocate for having some photovoltaic, mostly for the educational value, I'll call it the outreach value.
Okay, wonderful. Thanks very much. So this brings us to the end of this webinar, and I would just like to remind all of you that this webinar will be available for free on-demand download shortly following this live presentation. So you can either keep an eye on your emails for more information from Lab Manager about that, or you could visit the URL at the bottom of your screen. So on behalf of Lab Manager, I'd like to thank Matthew Fickett for all of the hard work he put into his presentation, and I'd like to thank all of you for taking time out of your busy schedules to join us today. Once again, thank you to our sponsors whose support allows Lab Manager to keep these webinars free of charge for our readers. Finally, I would like to invite all of you to attend the other webinars offered by Lab Manager's Lab Design Digital Summit. Tomorrow, we will begin the second day of the Lab Design Summit with a presentation from the winners of the Excellence in Innovation Prize in our annual Lab Design Excellence Awards. This case study of the University of Michigan Biological Sciences Building and Museum of Natural History will begin at 11 a.m. Eastern tomorrow, so please join us. For more information on all of our upcoming or on-demand webinars, or to learn more about the latest tools and technologies for the laboratory, please visit our website at labmanager.com. We hope you can join us again. Thank you again to Matthew, and thank you to all of you for being part of our Lab Design Digital Summit. We hope you have a great day.
Thank you.